Hi everyone, Mr. Boltri here bringing you video 2.7, where we're going to talk about average speed and average velocity, and specifically how to find these quantities on a velocity time graph, a position versus time graph, and using equations to find them too. So in order to talk about this, we're going to look at the example that we introduced in the last video and talked about in our last class. And that is of the car that drives forward slowly, hits a wall and stops for a couple seconds, and then zooms back in the negative direction. So you can see that in the position versus time graph with the shallow positive slope, which is a small positive velocity, a horizontal slope of the position versus time graph, which we can see as zero velocity on the velocity versus time graph, and then the steep negative slope, which we know is velocity, and see as a large negative number on the velocity versus time graph. So if the question was how do you find the average velocity using this velocity versus time graph? You might just use basic averaging principles from your math class. Let's say on the first test you got an 80, the second test you got a 90, and the third test you got 100. Congratulations. So what is your test average? Well, if we take the 80, the 90, and the 100, and we add them all together, and then divide by 3, we get 270 divided by 3. Your test average is a 90. So what we did is we took the cumulative sum and divided by the number of things that we added up together. So we can try to use the same thing here, as we have a velocity of 2, 0, and negative 5. So we're going to take those three velocities and then add them together and divide by 3. If we do the math on that, we get an average velocity of -1 tiles per second. And if we go back and make sure that makes sense looking at the position versus time graph, we move in the positive direction, stop, and then move in the negative direction. So this is what it would look like if it had an average velocity, sort of overall, an average velocity of -1. So this actually doesn't look like it represents an averaging out of these three things. It doesn't look right just because it doesn't look like it represents an average of a lot of positive, a little stopping, and then just a tiny bit of moving in the negative direction. Even though it was moving in the negative direction pretty fast, this just seems to be moving in the wrong direction entirely. So how are we going to fix this average velocity from a VT graph? Well, I was thinking about it, and using the averaging of the tests example isn't a very good example because all the tests are evenly weighted. But if you think about like your grade in my class, it would be like trying to average out a quiz with a test and a practicum. And we know that in your final grade, those three things have different weights, 50%, 40%, and 10% respectively. So and the same thing is happening here. There seems to be a lot more of the 2 tiles per second than there are of the -5 tiles per second. But in our equation, we've sort of weighted them the same. So how can we add sort of a weight to each of these to enable it to reflect that there's more 2s than there are -5s? And another way to say that is it was going at 2 tiles per second, had a velocity of 2 tiles per second for longer than it had a velocity of -5 tiles per second. And I actually noticed how much longer at a velocity of 2 tiles per second for 4 seconds and -5 tiles per second only for 1 second. So I actually added in by multiplying by 4, 3, and 1, which is the number of seconds it had each velocity. 4 seconds for 2 tiles per second, 3 for 0, and 1 second at -5 tiles per second. And then divide by 3 because there's 1, 2, 3 velocities. But actually that's a trick because we're no longer counting up the velocities. When we multiply by these weighted averages, we are now looking at what velocity did it have over how many seconds. So now since we have 4, 3, 1, now since we have 8 total seconds, we don't want to divide by 3 for the velocities. We want to divide by 8 for the total number of seconds. So when you do all the math out on this, and this is what's called a weighted average, where 2 has more weight than -5, has a weight of only 1 second. When we do all the math on this, it turns out to be an average velocity of 0.375 tiles per second, which if we go back to the position versus time graph, and we put, if we show an object using the purple line, moving at 0.375 tiles per second, that looks like it represents the data a lot more because the car moves in the positive direction, stops, and moves in the negative direction. And this purple line sort of represents the average of the motion of the car. So that's actually a good thing. So now if we go back and look at, well, what did we actually do? If we were to try to turn this into, let's say, an equation that we could use every time, what would that look like? So when we do 2 times 4, that's actually just the area of this rectangle. And then 0 times 3, there's no area here because it's 0. And then negative 5 times 1, again, the area of this rectangle, length times width. So we get 2 tiles per second times 4 seconds. And then same thing over here. And then that, if we do tiles in the, seconds in the numerator, seconds in the denominator, they're going to cancel and leave us with 8 tiles, 0 tiles, and negative 5 tiles. And hopefully you remember and or have it written down in your lab notebook that the meaning of the area of a velocity versus time graph is the displacement. And if you don't have that written down, then it's definitely worth writing down. Even if you have it written down, write it down again and put a big star by it, because this is a really important point. So when we do 2 times 4, we are just finding the displacement during the first 4 seconds. 0 times 3 is the displacement from 4 seconds to 7 seconds. And negative 5 to 1 is the displacement from 7 seconds to 8 seconds. So, and then if we add those all together, that's basically just the total displacement. Moves 8 tiles to the right, 5 tiles to the left, for a total displacement of 3 tiles to the right. So we can simplify that down into an equation, which is the average velocity, which is a weighted average, equals the displacement, which is basically all of these little areas, divided by the change in time, which is 8. Just to be clear, this equation up here, doing the weighted average, is the same as this equation down here. Because in order to do the weighted average, that just basically gave us the displacement, because the weighted average is the area of all these shapes, which is equal to the displacement. But again, something else that is definitely worth writing in your lab notebook is the equation for average velocity is displacement, or change in position, over change in time, over the time interval. And let's go back and make sure that that works on the position versus time graph too. So if we take that equation, change in position over change in time, the final position is 3, the initial position is 0. 3 minus 0 is 3 over the change in time interval is 8 seconds. So that gives us the same average velocity. And it all checks out. So that is how you would find the average velocity from a velocity versus time graph or a position versus time graph. All you need to do is do the change in position over the change in time, the displacement over the change in time. And this makes sense because this is one object that has one velocity that represents the average velocity of all these other velocities over the time interval. So it would make sense that they would start in the same place and end in the same place if they have the same average velocity. And that's actually a key important point in average velocity. If they start in the same place and end in the same place, then they have to have the same average velocity according to the formula. Let's do the same thing now for average speed. It's basically going to be exactly the same, except for speed, we don't care about the direction. So instead of having -5 here, we're just going to take away the negative. We don't care about the negative. So it's 2 tiles per second, 0 tiles per second, and 5 tiles per second. And then we do the math out on that, and we get this average speed of 1.625 tiles per second. And then if we look at the graph, instead of having negative area here, we actually move it up and have a positive area. So we don't care that these velocities in the negative direction. We just care that it moved 5 tiles per second for 1 second, which gives us 8 tiles, 0 tiles, and 5 tiles. Which, if you think about it, the absolute value or the magnitude of the area, not caring if it's positive or negative, that's actually going to be the total distance traveled. So a way that we can think about average speed is total distance traveled divided by change in time, which on a VT graph is just to take the area and then don't worry about the positives or negatives. Just take the absolute value of the area, and that will give you the total distance traveled divided by the change in time. What this looks like on a PT graph, well, we see that it moves 8 tiles to the right and then 5 tiles to the left. But again, for total distance traveled, it's like a Fitbit. We don't care if we're moving to the right or to the left. We still get the steps either way. In this situation, we still are traveling a total distance of tiles either way. So it's going to be 8 tiles, and then we're just going to pretend like instead of moving to the left, it just keeps moving to the right. We're going to take the absolute value of how far it moves. 8 plus 5 is going to give us 13. 13 divided by 8 is going to be 1.625 tiles per second, and it works here too. So to find the average speed, take the total distance traveled and divide by the change in time. If you didn't get them while I was on the slides, make sure you write down both of these formulas in your lab notebook, and you should be able to solve problems for standard 2C, either using the velocity versus time graph to find either of these two things, the position versus time graph, or you can solve it using a word problem. We're going to do some practice problems with both of these quantities next class. But for now, this is Mr. Boltri wrapping up video 2.7 on average speed, average velocity. Please make sure to write down any questions that you have, and we'll try to get those answered. And until I see you again, go Bears.